Welcome back. We're going to go through the conservation of momentum. Do we have to conserve momentum? Is that a thing? Hopefully you've already gone through the bits that we've already done, which are going through what the heck momentum is, why we're looking at momentum. And we did that with the Newton's cradle example. Then we also went through what momentum actually is, how do we get that, and we looked at that in parallel with our kinetic energy there. And now let's see if we actually need to conserve this. And the shortcut answer is yes, we do need to conserve it. So I'm going to label my notes here, the conservation of momentum. Or you might say momenta, since it's like multiple momentums. But it's usually just labeled as conservation of momentum. So let's get a real example. What if people are playing a sport? Maybe they're playing football. I don't know. Let's do football. Let's say that there's a little pipsqueak of a person, and they're playing football. And there's a massive giant. Oh man, look at their heads difference. Holy moly. And he's got a lot of muscle. Got leg muscle too. That looks really weird. Calf muscles. I should take drawing classes. Okay. Anyways, they're wearing some sort of helmet. This guy's wearing a little helmet too. He looks a little bit scared. And this guy is going to run into that guy there. So this guy has some velocity going forward there. We don't know what that is. And this guy has zero velocity here. Was similar to the last unit, we're going to identify some action. They're going to collide. That collision, that action is going to be the collision. And so then after they collide there, what's going to happen? What would happen? Who would win? And you'd say, oh, that little guy's probably going to get clobbered. And I generally would agree with you. But we're going to look at it from momentum there as well. So then they're going to be like, let's say that they're moving together. Let's do this. Let's say that the big person is so big and he's running so fast that he basically like picks up, but doesn't actually lift up too much, but like holds on to that person because maybe they're like, maybe they're like linebackers, or I don't actually know the terms and such. The people who like run into each other right at the scrimmage line there. Is that linebackers, fullback, or something like that? I don't know. Anyways, and they're like gonna, run in and hit each other like they, like you've seen on TV before. And this guy like pushes that guy totally back. So they're going to be moving together, is what I'm trying to get at. And so then they all have like some new velocity there, which we don't know. Beginning velocity over there, v naught. That wasn't a good zero. V naught. There we go. So let's look at this situation here. Let's look at from each perspective, both perspective of big person and perspective of small person. So this is big person and this one's small person. So I'm going to use I'm going to make up subscripts here, B for big person and S for small person. So let's look at from the big person's perspective, and let's look at it in the middle of the collision here. So this will be like actively during the collision here. If I think about it from the big person's perspective here, I'll go and draw a free body diagram for the big person. And clearly we'd have gravity's pulling him down, and we have the normal force, the ground holding him up there. Great. Let's assume that he's not accelerating up or down. And when he runs into the little person, well, let's go ahead and do the little person at the exact same time. Sometimes I kind of like doing that because I use the logic of the entire scenario here to help me fill out both. And I usually do actually do it simultaneously in my head. So little person has force gravity on him and the ground's still holding that little person up. They're not accelerating up or down. Great. Little person, do they get a force on them when the big person collides into him? Yeah. Which way does the little person get shoved? To the right. Yeah. So I'm going to do that in a different color to highlight that. Yeah, little person gets shoved to the right. Absolutely. And it's the force that's on the small person by the big person. Oh, cool. An on-by statement. I have two different objects here. On-by statements are really helpful to keep things clear. Now, what type of force is that, by the way? Well, running into there, it's probably going to be two surfaces pressed against each other. That sounds like a normal force. So yeah, it would actually be a normal force. So if you wanted to do F subscript N and then subscript S comma B, that'd be fine too. I'll just drop that for this case here. All right, so then big guy puts a force on the small guy. Great. Does the big guy, let's go back to the free body diagram of the big guy. Does the big guy feel anything when he puts that force on the small guy? Well, I mean, yeah, if you were that big guy, you'd feel something. You would feel that you ran into some smallish type of person, and you would feel force on your body and a force that would go which way? Well, yeah, it'd be a force like opposing your, running into him. And so that would be the force that's on the big guy by the small guy. Okay, cool. Yeah, because we think about that and we go, hey, if the big guy is like running here, would he be able to run as fast, if he ran into the guy or if he didn't run into the guy? If he was trying to win a race, would he want the guy standing in his way or not? And you'd say, no, clearly, if the guy wasn't standing in his way, it'd be easier to run faster. So running into somebody, no matter how small, is like slowing him down, you would probably say. Okay. All right, so then he's moving, the big guy's moving to the right, and he gets a force that goes opposite of that. Now notice that when I sum up the forces in the x direction here, I have an unbalanced force. What do unbalanced forces cause? They cause a change in motion. And we can go ahead and put it in the velocity vectors. The velocity is moving that way. Again, that's not part of the free body diagram, but I draw it next to there. So notice that I have an unbalanced force that goes opposite of that velocity there, and that also means that I'm going to be accelerating that direction because unbalanced forces, I'm doing Newton's second law in my head here, I should write it out. The unbalanced forces always cause some acceleration, and it's in the exact same direction. So then that force causes that acceleration, and when I have acceleration that points opposite of velocity, that thing must be slowing down. Okay, cool. So then this big guy slows down when he runs into the small guy. Great. Let's compare these blue forces there, though. Hey, which force is bigger? Yeah, the force on the small guy is bigger, right? Well, hold on, not so fast. Wait, hold on. Let's think about this. We have two objects, and they're touching each other. So big guy hits little guy really hard. Object A puts a force on object B. Well, then what must also happen? Object B must put a force on object A. That's right. So then if A, notice what am I doing here? I'm doing Newton's what law? Newton's third law, that's right. If A acts on B, then B must act on A. Okay, so then if, let's put it in other words, if A pushes on B really hard, then B must push on A really hard. Yeah, that's right. So then if big guy puts a huge force on the small guy there's the huge force, then the small guy must put a huge force on the big guy, and these forces are exactly the same. Huh. Interesting. So Newton's third law here does work, and it does apply, and if you actually went and measured this, which you did a lab and you did measure that with little force sensors, and you put masses on top, and they were like hooked together, and you're like dragging them along and at a constant velocity, accelerating, and so on. And you found that those forces were always the same, and they are always the same. We haven't found any exceptions to Newton's third law ever, period. You should find it. You would be very famous and probably make a lot of money, and it'd be great. But we haven't found one yet, and so that's true here as well. That's kind of odd in some manners, because when I just look, if I watched this happen in a game, I would go, ooh, I'd feel bad for that small guy. Small guy might get destroyed. And so a lot of times we get confused between the outcome of some sort of action, in this case the collision. The outcome might be that the small guy gets hurt, and the big guy probably doesn't as much. Well, if it's the same amount of force, wouldn't they both get hurt equally as much? Well, we're evaluating some more complex things here, like, hey, what about the strength of the small guy versus the strength of the big guy? And what I mean by strength, not necessarily with muscles, but like with bones. Maybe the small guy would break bones and the big guy wouldn't. Well, maybe the big guy's bones are literally just stronger than the small guy's. Oh, that might be true. Generally speaking, the larger the object, the more forces that can be put on them without breaking. That is a large overarching statement there that really isn't always true. But generally, when you're just interacting with things, if you take little small bolts and you twist them, it's easier to break those little small ones than it is to break, the really big ones. And so generally, when you're working with things, smaller things, you can't put as much force on them without breaking as you can larger ones. Now, that you can find exceptions for many, many different cases in that, because that's not always true. But in general, I think you would agree that that's fairly true. Okay, so just because one thing breaks or somebody gets hurt doesn't mean that it had more or less force on it. Okay, because there's like other things going on there. So it is true that they actually have the same amount of force, even if one gets hurt and the other doesn't. Okay, so if they have the same amount of force, let's get back to momentum. That's what we're doing here. Let's go and calculate what's going on with the momentum. So we're going to do two parallel ones. We're going to look at the big guy over here. We're going to look at the small guy over here. And what's going on with their momentum. Well, is the big guy's momentum changing? Well, big guy runs into small guy. You said big guy's going to slow down. We said, yeah, he's going to have some unbalanced force. It's going to cause him to accelerate, which is opposite of his velocity, so he's got to be slowing down. So now, if he's slowing down, what's happening with his momentum? Well, momentum is just the mass time, the change in momentum is just the mass times the change in velocity. That's what we saw from before. And if you're changing your velocity, you're going from, in this case, a big velocity to a small velocity. Maybe I'll write that out. You're going from big velocity down to a small velocity. Then maybe I'll make that difference a little bit bigger. Then we're going to be changing its momentum there. We're going to have some beginning or ending momentum. Wow, I just did that backwards. Holy moly, take a step back. Wow, we're going to do some ending momentum minus some beginning momentum. Woo, woo. We've been off of school for too long, I guess. And that's going to be equal to some ending momentum, which will be smaller, versus some beginning momentum, which is going to be bigger. Okay, cool. All right, so then he is going to be changing his momentum there. Great, great, great. Well, let's take a step back there, though, because we said, take a little bit step back from this, because the base equation that we found out from the last video there was that, hey, the amount of force that you put on that thing multiplied through some displacement there is equal to the change of momentum. Now, let me actually write that like this, because we just wrote it like that above there. So the amount of force on that thing through some amount of time is going to be equal to the change of momentum. So it's not just this force that we put on the big guy, but also the time. Oh, okay. So now if I was a bystander and I was watching this and somebody gave me a stopwatch, maybe I would time it. And the time when they're actually actively colliding and like running into each other, and if you watched it in slow-mo, like, their skin and muscles and such would be like compressing into one another, and you'd be able to see all that. Watch some of the videos on the slow-mo guys. I think they have of somebody punching somebody else like in the face. Don't do that at home. But it's interesting on a anatomical level of like what's actually happening with things squishing into each other. Anyways, if you were measuring the time that they were actually colliding, of impacting, of when they're actually squishing against each other, there'd be some amount of time. Even if it's short, it's some amount of time. And anytime you have any collision, including car collisions, there's some amount of time where it's actively like colliding, actively like things are compressing and changing and such, and that their momentum is actively changing, and that's truly what's going on. So it's the amount of force through some time of that collision, and that force through that time is what's actively changing that motion or that momentum, because that's what momentum is. It's just the amount of motion. Okay, so then let's do some tricks like we did before here. Let me substitute in. We're going to do this in the x direction as we did before, because that's the only case that is actually interesting here. That's the F. So let me put that as F. Let's do it in a different color so it stands out a little bit more. This is the force on the big guy from the small guy, and that's through some time there. Okay, great. And that's going to be equal to his change in momentum. And let's just get an idea here. If I did a ending momentum, which is small, minus a beginning momentum that's big, that's going to be a positive or negative quantity. It's going to be a negative quantity. I got a small thing minus a big thing. So I'm expecting this left side here to be negative. Maybe I'll write a note to myself that this thing is going to be some negative quantity there. Sorry, my pen doesn't work well on the edges there. Okay, so let's simultaneously go do that for the small guy. So the small guy over here, he's got some change in momentum of him as well. He's going to get a force going to the right there, and you'd say, oh, that guy speeds up some. Okay, cool. So let me kind of do that above here like I did with the big guy there. So he's going to have some ending velocity, which is going to be bigger than his beginning velocity, which is really small. His beginning velocity was actually 0 in this case. And similarly, his ending momentum is going to be big, and his beginning momentum is going to be really small. And in this case, we'll just go ahead and put that in. His velocity at the beginning was 0, and therefore his momentum at the beginning was 0. Okay. So that means that this change in momentum here for this guy, as he changes momentum, that's going to be a positive or negative quantity. This thing is going to be a positive quantity. He's speeding up there, right? And so the big guy is slowing down, little guy is speeding up. Interesting though. One's negative and the other's positive. Okay, let's keep going. So now we'll put in the force, and so the force on the little guy, that's the force on the small guy by the big guy, and then multiplied through some delta t. Now notice that from our free body diagrams, we had both the force on the small guy and the force on the big guy. And we said that those forces were equal, meaning that this force in blue down here is equal to that force in blue over there. Maybe I'll write a blue statement in between them, or blue statement in between them, reminding myself that the big guy, the force on the big guy is equal to the force on the small guy. Now, technically, I'm going to leave this out right here, but technically they're equal and opposite. One's going to the right, this guy's positive. One's going to the left, that guy's negative. I'll go ahead and I'll put it in actually. So equal and opposite, the opposite in direction, but the same amount. Okay, so don't let the negative throw you off there. So now let's compare that. So let's look at the right-hand side still. These F's are both the same. And then the delta T, are those the same? What's the time for what? What's the time for those guys colliding? And if you were that innocent bystander who was measuring that, maybe in a slow-mo camera or something like that, of when they were actively like colliding and like putting that force on each other, would it be the same time for each of these guys, or would it be a different time? Yeah, it'd be the same, right? There's only one collision there, and so you'd measure it. You could say, oh, you could give a timer to one person, say, measure it for the big guy, and a timer for the small person, or to another person, say, measure for the small guy, and they would come out with the same value, assuming they're watching the same slow-mo video or something like that. Or maybe you should give it to a bunch of people, because in actuality, you probably get slightly different values. But you get the idea, is that there's only one event here. There's only one action, so there's only one time for it. So that means that the delta t on the left side there is equal to the delta t on the right side there. Wait, hold on. Wait. That means that this right-hand side equation over here for the small guy is equal to the right-hand side equation for the big guy over here. But then that means that the left-hand side of the equation for the small guy has got to be equal to the left-hand side of the equation, except for one little thing. This little negative here. Oh, okay. So that little negative, let's go drop this line down here, and I'm going to, instead of writing the force on the big guy from the small guy, I'm going to go ahead and I'm going to replace it with that. I'm going to just add, I'm going to add that negative in there. So, well, maybe I want to do it like that over there. Well, let's talk about it. And then I'll write it out. I don't want to confuse you. So they're the same amount of force. So the right-hand side is exactly the same, except for this little negative sign that's in over here. And what does that negative sign do? Well, that means that the left-hand side is going to be the exact same value as this left-hand side over here on the small guy, except that the big guy has a negative of the same number as the small guy does of the positive bit. Oh. Why is that? Oh, we said that one was negative. We expected that because the big guy slows down and the small guy speeds up. Well, where did the small guy get that motion from? Small guy got the motion from the big guy. Let's write some generic statements, and then I'll go back and add some of that math there. So, big guy gives momentum remember that's just motion, to the small guy. The small guy increases his momentum by the same amount as the big guy decreases his momentum. The big guy's, let's write it like that, the big guy's momentum decreases. So let's read that one more time. So the first one, the big guy gives momentum, which is just motion, gives motion to the small guy. Okay. Well, now if the big guy gives motion, big guy doesn't have as much motion, and so the big guy is slowing down. So the second statement here is kind of saying that in different words. Small guy gets more motion, increases his motion, increases his momentum. But the big guy then must decrease his motion because he gave some of that away. And so, well, however much the big guy gave away of his motion, the small guy increases by that amount. Well, now, wait a second. If one object, in this case, the small guy, increases his motion by the same amount as the big guy decreases his motion, did we destroy any motion? No. Oh. So this gives rise, what we just proved here, is that momentum, that's terrible, momentum cannot be created or destroyed. Momentum cannot be created nor destroyed. Anytime that this statement, something can't be created or destroyed, we say that this thing that can't be created or destroyed, we say that this is conserved. Conserved means it's not increasing or decreasing, it's not changing. That's the mathematical or physicsy way, sciencey way to describe this statement here. So we have a conservation of momentum. We are not losing it. We're not gaining it merely. It is always the same. So we have conservation of momentum. Momentum can't be created or destroyed. Can it be transferred? Yeah, it's transferred from the big guy to the small guy. Great. So you can give it from one object to another object, and that's it. Now, some notes here. Some notes is that there's no types of momentum. In energy, there was tons of types of energy. There's kinetic energy and gravitational potential energy and thermal energy and all these different types of energy that you had to worry about. In momentum, it's much simpler. In momentum, there's no types of momentum. It's just momentum. No types. So in general, it's like way easier to do calculations and to assess collisions, especially with using momentum than it is in energy. And energy can be hard and tedious, as you found in some cases there. And momentum is generally a little bit more straightforward. Oh, cool, great. So in summary here, we used Newton's third law to show that the amount of force on each object is exactly the same. And because that's true, and since that's always true, then the amount of momentum can't be created or destroyed, because otherwise, if I was creating and destroying momentum, these amount of forces here wouldn't be the same, and then Newton's third law wouldn't be true. And it's not that we really love Newton's third law, and that's why we don't want it to be true. Instead, when I go and measure the world, this is what we get. Every time that we measure the world, we get that the momentum doesn't change, and therefore the Newton's third law must be true, and vice versa. When Newton's third law is always true, and therefore momentum isn't increasing or decreasing. Cool. Some other notes here. Some kind of tips and tricks. If you're looking at collisions, if you're ever looking at collisions, you should be thinking momentum. Momentum is like the king for analyzing collisions here. Why is that? Well, basically it comes down to, if you looked at it from energy, if I had kinetic energy coming in and something colliding, where's that kinetic energy going? Well, it could be going into the kinetic energy of that other object. So let's use this example here. Let's try and do it with energy, this same thing. You go, big guy runs into little guy speeds up, little guy increases the kinetic energy, big guy decreases in kinetic energy. But if we look in actuality, is kinetic energy the only thing going on there? Well, no, like they're colliding, so like their atoms are going to wiggle and jiggle, and they're going to like heat up some. Okay, so there's some amount of thermal energy. How much thermal energy? Where did the thermal, like how do I calculate that? And a lot of questions come up, and there's more than just even thermal energy, but even just with that, we go, I can't solve this problem. However, think about it from momentum, and you go, even if things heat up, that's great. The momentum itself has to be conserved. And so I don't have to worry about any of that stuff. I just know that the motion of the big guy is got, and here's another way to think about it, is if I made my system, if we do this problem just a little bit differently, and I make my system both the big and the small guy, then now I have all the objects that are interacting and all of the objects that are transferring their momentums with each other. And in that case, I can know that the change in momentum of this entire system here, both the big and the small, must be 0, meaning we can't create or destroy momentum. And that means that, well, let's expand this out on the left side there. That's the momentum at the end minus the momentum at the beginning is equal to 0. Another way to say that, let me move that over to the other side, and then I get a negative and I multiply. Well, let's just do it together. If I move that over to the other side, then I can drop these negatives here. I'm going to just multiply by -1. And I see that the beginning momentum of both the big and the small must be equal to the ending momentum of both the big and the small. Oh, meaning that I didn't create or destroy momentum here. Okay, cool. So then, like, whatever momentum I had at the beginning of this situation here before they collided, it's got to be the same amount of momentum as both of them, in this case, together, because you just like kind of carry them there. It's got to be the same momentum afterwards, right after they collide. And that's oftentimes an easy way to solve them. Solve any of these problems is you can make the system both of these things. Now, you could make the system the big guy and the small guy separately, as I did down here. And as I went through here, I saw that, hey, the change in momentum of one of these objects was negative and the other object was positive, meaning what if I added both these things together? You're right. If I added both of these things together, I'd get a change in momentum that is actually 0. Okay, now last little bit, let me move that down there to get the change of momentum is actually 0. If I add both these together, just like the system that was in purple was both of those, I said that I was going to add in this negative bit here. So I'm going to go ahead and I'm going to, I'm going to move this negative sign. Oh, let's move that over here. I'm going to multiply -1 on both sides there, so I have the big guy on the small guy is equal to the negative of the small guy on the big guy. You'd agree that I didn't mathematically change anything. Now I'm going to go and take this thing and I'm going to plug it in for there. So I'm going to replace the force on the big guy by the small guy with the opposite of the other one. So now I have negative. Let me do the negative in red there. So now I have negative of the force on the, well, maybe I should keep that blue, force on the small guy by the big guy, since I just substituted that in, times delta t is equal to my change in momentum there. And so I go and I compare that with this equation that I have right there, and let me just copy and paste that down so we can see it on the same line there. And I go and compare that. This guy goes. And when I compare that, I go, hey, yeah, that's right. This says that if I know that this one's going to be positive, then this guy has got to be a negative, this guy has got to be a negative quantity over there, because it's the same exact line, except it's got that negative sign in there. Okay, so then like mathematically that works out. If we put in real numbers, mathematically it works out as well. If you go and try some of those problems and look at my solutions there as well, you'll see that it works out with the numbers. Cool. Okay, that's it. That's all my little tips and tricks and notes for there. Hope you have a beautiful day. See ya.